Okay, so the last lecture was about nuclear weapon effects, and now we're going to continue with other effects which are horrible. And we're going to also talk about also some nuclear testing and so on. So after the bomb, as I explained to you, the partition of energy is this way, where you have 50% of the energy is in terms of blast wave, 35% is thermal energy that's released, causing these fires that we discussed, and 15% is the nuclear radiation, and that's what we're going to focus on next. So the radiation effects are 50% of the total energy released by the bomb. So what happens is, for example, something like an airburst that you see here. If you happen to be underneath the airburst, then you'll, as I mentioned before, you'll die because of the blast wave effect. But you won't actually necessarily die of the radiation. And the reason is because the gamma rays and the neutrons can't necessarily penetrate so far to the ground. And on top of that, this fireball itself will start to rise very quickly like a hot air balloon. And so it just won't catch you. The blast wave will, but not the radiation. But the problem is that you'll also produce a lot of fission products. Remember, this is what's released after the isotopes split and fission, and they split into 2 and 3 pieces, and then these are going to be radioactive. So for example, cesium-137 or strontium-90. These long-lived isotopes will hang around for a very long time and get in dirt and that kind of stuff. And then you can also have a fallout cloud which carries some of this radioactive residue for long distances and can drop it in different locations. Long distances or short distances, that really depends on the configuration and type of bomb and so on. So radiation, initial radiation is released within the first minute. These are prompt gammas and neutrons. They penetrate deep to the ground from the rising fireball. If it's an explosion on the ground, then it will be even more of an effect. There's going to be short-lived fission products which will very quickly decay. Basically within 10 seconds, a lot of the isotopes will have been decayed, but there's lots of other stuff that tends to hang around for a very long time. But the effect is much less, this prompt effect is going to be much less when it's an airburst compared to a ground detonation. And that's the reason why essentially it's possible to live in Hiroshima right now, because it's not so much contaminated as other places, as it would be if it would have been, you know, a ground detonation. And then you have the residual radiation, which remains for a long time, which is caused by what's called neutron activations. And this is when neutrons hit different materials, ordinary materials, and then make it into radioactive materials. So this turns rocks that were not radioactive before into being radioactive. And it turns all kinds of things, makes things essentially radioactive. The decay of fission products are longer lived. The fallout cloud can travel very high into the atmosphere, and if detonated at low altitude can produce deadly early fallout. So the effect of the fallout is going to be considerably less if it's older. So if the material is older, a lot of it will have decayed. And so the effect is not going to be so damaging to the body. But if it's detonated at a very low altitude so that the rain washes it out and it ends on the ground quickly, then the effect can be very dramatic. And this will include many different things like the bomb debris and the different activated components, so the neutron activation that I talked about and so on. And fallout patterns themselves are complicated. They can be only really predicted by complicated computer models and so on. So again, I always show you these horrible images by the people who've survived the bombings. paintings. So after the bombings now, let's switch directions a little bit. What was the legacy of all this nuclear testing that was being conducted? So after the bombs, physicians project that some 2.4 million people worldwide will eventually die from cancers due to the atmospheric nuclear tests that were conducted between 1945 and 1980. These numbers are very, very large, but if you think about the amount of bombs that were conducted, 29,000 Hiroshima bombs, and then if you think about it, that there were a few kilograms per bomb, and that this material disintegrated and became fission products all over the place, then it's not hard to see what incredible damage this would have done. Now, it's not always possible to figure out who died because of cancer due to a nuclear test that was conducted or due to other effects, because unfortunately so many people get cancer, and it's so hard to pinpoint what the reason was for getting the cancer in the first place. But this is an estimate that try to estimate what is the kind of statistical effect over the entire planet from all this nuclear testing that was conducted over the years. Right now, happily, we're in the period of a moratorium. Hopefully, North Korea will observe it, and that other countries will also continue to observe it. Here I have a book recommendation, which is Radioactive Heaven and Earth. It's free. You can find it online. And the estimate that I showed you earlier is based on these numbers done by physicists and health experts and so on, to try to get an understanding of what the effect was of all this nuclear testing over the years. But that's not all when I talk about the legacy of nuclear testing. When the nuclear testing was conducted in the Marshall Islands by the United States, there was the hardtack-1 cactus, an 18 kiloton TNT test, which produced a large crater. So a lot of the radioactive materials that were used in other tests that were conducted in the Marshall Islands were just basically dumped there, containing 84,000 cubic meters of radioactive contaminated soil and 46,000 cubic meters of contaminated debris from other nuclear tests were basically dumped in this dome and covered up. Why I always say that nuclear testing is so complicated is there's many different effects. Now we also have to consider the effect of climate change, because as the waters are rising in the Marshall Islands, the fear is that some of this dome won't hold, and some of the radioactive materials will go into the water. And this is a tweet from October 10th, 2019, where Dr. Hilda Hein, who is the president of the Marshall Islands, said that our parliament has officially declared a national climate crisis as one by only 4 low-lying coral atolls nations in the world. The failure of the international community to adequately respond to the climate crisis of its own making holds particularly grave consequences. So we can't really separate the effect of nuclear testing and climate change. When the two come together, it's a very dangerous effect that I'm personally very concerned about. There's many other effects than we talked about. We talked about blast wave, talked about radiation, all kinds of other things. But there's also the emergency response is not going to be necessarily very good. There was a recent study by the Norwegian Radiation Protection Agency that found that adequate countermeasures to a nuclear detonation simply don't exist, even given the vast resources Norway has. No official UN organization mandate is to deal with such an effect, and no specific UN or interagency planning or exercises conducted to prepare for a nuclear detonation. While there have been radiological incidents, such as the dirty bomb scenarios, there have been plans. So the problem is that there's really no plan for dealing with all these different effects should a nuclear bomb happen. Now I'm going to talk about the resurgence of the nuclear winter concept. It turns out that this idea of nuclear winter, that there would be, if you would have a nuclear exchange between the United States and the Soviet Union, which was emphasized in the 1980s, and a nuclear exchange between the two countries, that would produce a lot of soot in the air, and that would cause massive cooling of the planet. And the cooling of the planet would be, cause problems with the with agriculture, growth of food, and all kinds of terrible things. But people did that effect kind of went away. People didn't believe it. There was also kind of a lobbying effort on the part of people who were pro-nuclear weapons and pro-nuclear testing and so on. And also, I should say that the computer programs that they had at the time were not as good as they definitely are now. Well, since in 2009, Alan Robock and Owen Brian Toon have done recent studies of small-scale nuclear war. And this is a small-scale nuclear war between India and Pakistan of 100 Hiroshima-type nuclear weapons. So that's only 0.03% of the nuclear weapons that exist on the planet. And the effects are devastating. There's at least 20 million deaths, but that is not all. There's a nuclear winter effect that really is very significant. Now, these scientists were able to use current climate change models that are used by the International Panel on Climate Change, and were able to test the effect of what would happen if a nuclear bomb would go off and soot would go into the air and would block the sun, and so you get the sun wouldn't be able to get down to the earth, and you get massive cooling. So you get massive amounts of smoke and soot from fires that rise into the upper atmosphere and block the sun. The recent research is that a small nuclear exchange can lead to devastating climatic effects. The sunlight would be reflected back into the space, and you get rapid large drops in global surface temperatures, and you get collapse of basic life-sustaining ecosystems. And this shows you what would happen. This is the temperature anomaly due to climate change from the 1880s going all the way up to 2009. And there you would see what would happen if there would be this dramatic effect on the climate. It would be very rapid cooling. The growing season around the world for different crops would be shortened, not allowing them to reach maturity. It would lead to an increase in the price of food, mass starvation, hoarding by countries that have the funds, disease, war, competition for food. An estimate has been done how many people would be at risk of dying, and the number is as high as 2 billion people. So it would be enormous, even if you would have this small nuclear exchange of only 100 nuclear weapons between India and Pakistan. The problem is that cloud of soot that's produced by all the fires that would be produced would travel over the entire planet and would cover up the, would prevent the sunlight from getting to the earth. It's not only that, you also get UV depletion from the from an effect like that, where you have increase in local temperature high up in the atmosphere where the ozone is, by at least 50 degrees Celsius. This draws in nitrogen oxides, which actually depletes the ozone layer, which obviously has terrible effects like damaging terrestrial oceanic plants, producing skin cancer, eye damage, and other health effects in humans and animals. So this is just a summary of the effects of nuclear weapons. I have the destructive blast wave, which is intensified by an airburst, thermal energy, which can cause burns and mass fires, initial radiation burst, which produces neutrons and gamma rays and other particles. And a lot of these particles would be stopped if it would be an air burst. Residual radiation, and that, fission products that tend to decay. And you would expect little medical response. So unfortunately, a lot of the people who would be in a zone where the nuclear weapon would be detonated, a lot of people would not get the medical response. And on top of that, you also have these horrible climactic effects that really mean that even if India and Pakistan detonate, have an exchange of 100 nuclear weapons, everybody is responsible for making sure that something like that should never happen. We all have a stake in it because it affects us all. It's not that if India and Pakistan did it, or if North Korea and the United States would do it, it wouldn't affect Russia or something like this. No, we all have a stake in making sure that these nuclear weapons are never used again. So these are just some resources. And that's the end.
Okay. Thank you so much, Ferenc. That was a really comprehensive lecture. So for the many teachers and students may be watching these lectures, recorded videos. So for the sake of a conversation, I just wanted to ask some questions for the sake of a discussion. But first of all, just the impression, I really think the understanding the scientific impact, the real impact of the use of nuclear weapons, if you understand the actual impact of the use of nuclear weapons, this really enhances your understanding of the real humanitarian impact of the nuclear weapons. So that's why it's so important to understand what really happens. Of course, as a lay people, in terms of science, like me, it's very difficult to completely understand the details of the scientific impact, but it's very important for everybody to have a general idea on the actual impact of the use of nuclear weapons. You said maybe I should start with the backward, like your part 4. You highlighted there is no adequate countermeasures once nuclear detonations happen. And this is very true, and the International Red Cross, like a Committee on the Red Cross, ICRC also gave a similar a report, because the ICRC is the first one to go to the Hiroshima after the bombing in 1945. So that's my initial impression. But let me go back to your, I think this was part 2, when you talked about fissile material. There was some chart that how many fissile material is necessary, and you also said the barrier is getting fissile material is quite high. That's the important part of creating nuclear weapons. So in this regard, I think it is very important to understand how difficult it is to get the fissile material, or it is possible to have a fissile material. So can you just briefly elaborate if is there any measure? This may be a little bit different topic, but just briefly talk about some existing measures to prevent spread of fissile material.
Okay, so let me just take 1 second and talk about how the fissile material is produced first, because I didn't cover that so much. So first of all, if you're looking at the isotope uranium-235, which is an isotope which is very rare in natural uranium. So if I would look into the ground and look into the water anywhere, the uranium that I would find would be made of principally of 2 isotopes. One is uranium-238, which doesn't sustain a chain reaction, and uranium-235. And the uranium-235 proportion is only 0.7%. So that is not enough for a bomb, where you need to be higher than, let's say, 90%. So what you need to do is you need to enrich it further so that the fraction of U-235 compared to U-238 is going to be as high as 90%. So that's the first thing that you need to do. And so then if you have that amount of material, if you assemble that amount of material, then you can use that for even a gun type bomb or something like this. And to prevent basically the enrichment process itself is rather complicated. And although a lot of the information about how to do it is out there, it also takes a lot of energy, and it's hard to do it without knowing that somebody is doing it. That may not be true in the future, but it's generally true right now. The other isotope, fissile material, is plutonium. And plutonium is not found in the ground, like, for example, uranium is, but plutonium is produced in reactors. So U-235 is 0.7% of uranium. The rest of it is uranium-238. Well, that material, which is, almost all of uranium that you find in the ground, that material itself can be converted into plutonium. So if you put that in a reactor where you have tons of neutrons flying around, you can produce, the neutrons will hit uranium-238, which there's the most of them, and the U-238 will, over a few steps, will convert to plutonium-239. So you're producing plutonium-239 inside the reactor. Okay, and so once you produce it inside the reactor, you're producing this plutonium-239. Then, as I was saying in the lecture, if it captures another neutron because it's sitting in the reactor, there's neutrons are everywhere, then it becomes plutonium-240. And that was the discussion that I had about reactor-grade plutonium versus weapons-grade plutonium. Okay, now, in terms of how do you prevent, manage so that people don't take that material or something like that. So in the case of reactors and the fuel cycle itself, you have safeguards. So IAEA safeguards, which inspect the reactors to make sure that that material, because once the fuel itself that you use in a regular power reactor is used in the reactor, then a portion of that, 1 or 2%, is going to turn to plutonium. So you want to make sure that whoever owns that reactor or whatever doesn't take that fuel out and then do a process called reprocessing, where they separate the plutonium from the spent fuel. And that's why safeguards are there to prevent that from happening. So there's kind of this barrier, which is in the case of HEU or highly enriched uranium, or in enrichment process, which is, it's complicated. It's kind of a skill that's involved, which is, it's complicated to construct these enrichment plants to actually produce the enriched material. And in the case of the reactors, it's safeguards there. I mean, there's safeguards everywhere, but really those are the barriers. The other thing is you can always steal the uranium-235. So that's why it's important to be able to secure all that material in different vaults and facilities and make sure that it's either not used anymore, so that you have alternatives, so you don't need to use highly enriched uranium, which is another huge process that's going on in the world, which is to convert reactors that have highly enriched uranium as fuel or use HU in some purpose, that they're going to be converted to use what's called low enriched uranium, where it's much lower in the percentage of uranium-235 compared to U-238. So does that answer the question a little bit?
Yes, thank you. So I remember long time ago, 2009, when President Obama made a famous Prague speech. I hope some of us CIF students or teachers remember this speech. I remember when in his speech he said like a size of an apple of plutonium could destroy this city, like a Prague.
Right.
So 1 kilogram is a plutonium is a is that correct to say size of apple?
1 kilogram is even smaller.
Smaller.
Yeah. The density of, if you think, the way you can think of this is thinking in terms of water. If you think about water, the density of water is 1 gram per centimeter cubed, something like that. So that if you have 1 liter, it's equivalent to 1 kilogram. If you have 1 liter volume of uranium or even plutonium, it's equivalent to 19 kilograms. Do you see what I'm saying? So it's so vastly dense. It's 19 grams per centimeter cubed is the density of plutonium. So it means that you can have very small volumes occupy a lot of weight. So if you're talking about 1 kilogram, I don't know how big it is, but I bet you it's smaller than that.
I see, like a plum size of a plum.
Yeah, size of a plum probably.
Okay, thank you. Yeah, okay, so other interesting fact that, of course, there are so many things to learn, but other interesting fact is we learned is blast effect is not linear. And you said this is a bit counterintuitive.
Yes.
So, like compared to 10 kiloton bomb and you said 1 megaton?
Yes.
Yeah. So, but it's not 100 times like a blast effect. So this,
exactly.
So I came to some question. So what's the main difference between smaller nuclear weapons, like a Hiroshima type, and the modern nuclear weapons, like a megaton size bomb?
Right. It's really design. So, and it's very different from, let's say, chemical weapons or other things where it's just the amount of agent that you have, that's the big effect. Well, you remember the example that I said is that if you have 8 kilograms of uranium-235, there's 8 kilograms of uranium-235, that would produce a 1 kiloton bomb, according to that table. But then if you just multiply that times 2, that's 16 kilograms, right? Only times 2, but that produces a 20 kiloton bomb. So it's even that's not linear, right? So that's really the main point. So it's really about the sophistication of I hate to use the word sophistication when you talk about nuclear weapons, but it's the engineering, the experience, the capability of the country in building nuclear weapons. That's really the difference. And you saw that so nicely in that chart, is that it's not so much about the amount of materials, like it would be like if you would want to have a larger effect of a chemical weapon, you would have more agent, more material. But here it doesn't scale that way. It's really about the design of the weapon. So if you go, and this is a very good question, Masako. This is our concern with North Korea. If they went from an ordinary fission bomb then to boosting with their nuclear testing, and now we think they've gone to a hydrogen bomb, and that's why they were able to produce this large, whatever sized 300 kiloton TNT bomb explosion in 2017. So it's really about the design. And of course, the reason why you do nuclear testing is to try to optimize the design, and also to have larger yields, safer, and all that other stuff, but also make it smaller and smaller and smaller so that you could put it on a missile and in a nose cone of a missile, and so you can actually use it in a viable delivery system. So yeah, good question.
Thank you. So you also introduced a very good resources, nuke map. Now I think everybody loves this nuke map. Everybody wants to introduce this map made by Alex Wallenstein. So I'm sure that he put all those information to correctly demonstrate the impact of the use of nuclear weapons. Am I correct?
Yes, yes. Right.
Wow.
You can go to Nuke Map and put in whichever city you want, and see what the difference would be, what the effect would be in your neighborhood, if you had a certain type bomb compared to another type bomb, and you would be able to see, because what Alex Willerstein did very, very well is he included a population map, population density. So you can also see how many fatalities there would be, taking into account the size of your city and all that kind of stuff, where the population centers are and so on.
Great, thank you. And also you correctly answered some question, because I'm also often asked about the Hiroshima. Some people asked me that, is it possible to live, why people can live in Hiroshima after the bombing? And of course, there are lots of difference between Hiroshima bombing and the nuclear accident. At the same time, perhaps this is still very difficult concept. For example, maybe some of you teachers, students might have watched the recent HBO series Chernobyl, and of course, exclusion zone, you cannot go back even after 30 years. Is it 30 years? Yeah, almost.
Yeah, long time.
Long time, yeah, it will happen in 1986, yeah, right? So maybe, I know you, in your lecture, you explained, but could you reiterate, like maybe with some comparison between Chernobyl and Hiroshima, or in whatever way you could,
Yeah, I think I can do that. So the main point is this: once you get a nuclear bomb and it's detonated at a certain altitude, right? So it's detonated at, say, 500 meters up high, and you get the explosion happens. Then the first thing is that the prompt effect of those particles that are streaming from the bomb, they just don't make it to the ground. So you don't have the same effect as if they were detonated on the ground and you got this neutron activation that I talked about and all the other different effects. So you don't have that. But the other effect is since you're detonating the explosion at a high altitude, you produce all this debris, all these particulates that are highly radioactive and highly dangerous, the fallout, that will just travel very far away. So it won't actually settle where Hiroshima is. It'll settle in other areas, and it'll depend on what the weather conditions are going to be like, right? So that's really the main point. Whereas something like if you had a ground detonation, or you had something like Chernobyl or something like this, well, you also got a large fallout cloud, but it actually, a lot of it settled, a lot of the larger particulates that came off, little rocks and so on, it actually settled, as far as I understand, a lot of it settled also in Pripyat, which is very, very close by. So it depends on the weather conditions. It depends on how high it was exploded, what type of bomb, and all those things all matter in terms of the effect. But the reason why Hiroshima is kind of okay to live there now is because the prompt effect was not so large, and the although the devastation was awful in Hiroshima, it's other areas, surrounding areas, wherever, where the radioactive particulates, the fallout, settled on the ground and made people sick.
Great, thank you. So this is not really a question, but when you talked about nuclear testing, I came up with some recommended movie. I'm gonna include in the useful resources, but the Where the Wind Blows, the movie of the Kazakhstan, the Semipalatinsk nuclear weapons site. This is really powerful movie to understand the effect of the nuclear testing. So this is highly recommended. So.
Oh, and Masako, White Rain, not testing, but the White Rain, what's the name of the?
Black Rain and White Light.
Yeah.
White Light and Black Light.
Yeah, that's such an incredible movie.
Yeah, there are so many nuclear movies which is very scary, but of course, if movie is scary, but it's very important to understand the effects of the nuclear weapons. So this really comes to the issue of low-yield nuclear weapons that many politicians in certain country is talking. So this really gives you some misleading concept. If it's low yield, it's usable. So for example, if you are asked or you were told by someone who advocates low yield nuclear weapon is usable, it doesn't have a lot of damage, it's just a war fighting effective tool or something like that. How would you respond to that kind of a statement?
Well, we hear this now all the time. The effect will be less than larger yield explosions, but the worry is that it'll just kind of, the few, I guess. The one is that it'll escalate so that people will use, more of these smaller explosions, smaller nuclear weapons, but also that it's just going to be a slippery slope to using more and more and more and powerful yields. And we don't know how countries are going to respond. Let's say we take the example of North Korea. Say, and this gets back to the bloody nose scenario that was suggested by the Trump administration a while back. Let's say that you say to the North Koreans, we're using a low yield nuclear weapon to destroy a particular bunker or something like this. There's no way that they can tell whether it's a low yield or whether it's a large yield explosion. It's just impossible to know, and especially during the fog of war. So you would expect to get massive retaliation. So the concept of that it could be used as a battlefield weapon is very dangerous on many levels, because we don't really know how another country would really respond to something like this.
Thank you. So my final question is, could you please give some your advice to all these high school students, especially who are not so good at science, how you could study science and physics? Because I already regret that I didn't study physics very much at my high school age, and but I now really think it's very important, even if you don't become a physicist. It's really important to have some basic science. So maybe you could encourage those high school students who may not a big fan of science, but it's important to understand nuclear issues.
Right. Well, I would start by saying that you don't have to be an expert on the science of nuclear weapons and all that stuff. You just need to know a little bit to have an opinion about it. And the example I always use is like, I'm using a laptop, or I'm using a computer, right? I don't need to know all the inner workings about how the laptop works, but I definitely have an opinion on cybersecurity and those kinds of things. So I would say that I would encourage students to read a lot about this material, but don't feel that you have to know everything. There's lots of things to learn. But you don't have to know everything, just all the science. But I kind of try to emphasize the things that I consider to be important. But there's all kinds of good books that are out there and all that they can describe this in more detail and at different also at different levels. Sometimes more detail and sometimes a little less detail if that's what you want. But that doesn't mean that you shouldn't have a strong opinion about the topic. You don't have to know everything. That's I think what I wanted to emphasize.
Great. Thank you so much. It was really comprehensive lecture, and I hope students and teachers understand. And if you have any questions, please contact us, and we will do our best to respond to your questions. So again, thank you so much, Ferenc, for your lecture, and thank you.
My pleasure.
Thank you for listening and watching this lecture. Thank you. See you in the next lecture. Bye.